Okay, time to get started. So last time we were talking about change of variables. Let me just remind you, we did a whole bunch of stuff with change of variables, but it was all two-dimensional. Right? So we're going to move now to 3 dimensions, and here's the really good news. It's exactly the same. It's practically exactly the same anyway. Of course, it's 3-dimensional instead of 2-dimensional, but it's pretty much the same. We're still going to be looking at undesirable domains. And let's just take a moment to recognize what a nightmare this would be. Think about how to slice that up, how many corners you would hit, how many corners each of those slices would have, right? And other forms of undesirable to that shape. It remains that we're going to be viewing it as an image. It remains that we're going to be pulling back through that function to get a new, hopefully more desirable domain, such as perhaps, fingers crossed, maybe a rectangular box. Wouldn't that be nice? And it remains that the formula for the stretching factor is the absolute value of the Jacobian determinant. Same formula. Seems kind of weird. Now, of course, that's now a 3x3 matrix instead of a 2x2 matrix, right? But it's still the determinant, and it's still the Jacobian, the derivative matrix. Now, by the way, how do you see that that's the case? Well, you're going to make an argument a lot like this, and this is a fantastic exercise. I want to encourage everybody to give this a try. Just make a 3-dimensional version of this. You're still going to have, well, it's going to be a parallelepiped that approximates the region. It's going to be an image of a rectangular box. The edge vectors are still going to be the results of multiplying by the derivative matrix. The volume will still be an absolute value of a determinant, and the algebra works out, again, very simply. So this is very doable, right, to confirm that this is the stretching factor. I think it's a really healthy exercise. I hope you'll give it a shot. By the way, note the notation down here, again, pretty analogous and highly desirable for the same reason. And again, even though it gives me the willies just a little bit, it's as if those cancel. They don't, but it's as if they do, and it's a nice way to keep yourself going the right direction and keep everything straight. And let the notation do work for you. Okay. All right. Now, to lead into an example that uses this, I'm going to note this theorem here. This says that if you have a linear transformation, and don't forget, when you have a linear transformation, you can represent that transformation with a matrix. Right? So flashbacks to linear algebra. Flashbacks to the review that we did on like the first day of class about linear algebra. The derivative matrix of the transformation is the same matrix, as it turns out. Now, this is not hard to confirm. You can totally check this yourself. I encourage that you do this. You don't have to do it in general, sort of, n by m, but it's really easy. Just write down a 3x3 matrix. Write down the resulting linear transformation. Find the derivative matrix. Lo and behold, it's going to be the same matrix. It's a pretty straightforward calculation. So make sure you can do that. As always, if you're not sure how to get started, if you get stuck halfway along the way, if you're not sure how to interpret your words, if you have any problems at all, come to my office hours. I'll be very happy to help. No problem. But it's a good calculation to make sure you're comfortable with. Okay, so with that in mind, here's the example. This is a powerful example in the sense that we're going to take a question that would otherwise be just brutally difficult, and we're going to turn it into an easy calculation. So the brutally difficult example that we're considering is that we have a domain that is a parallelepiped, like this. Certain edge vectors having been given. So those 3 edges define what parallelepiped we're talking about. And we want to compute an integral on that domain. So this domain is, is our domain for a triple integral. Arbitrarily, I just made the integrand z, whatever, who knows for what reason we might want to do such a thing. But again, some application leads us to this triple integral. So how do we compute it? there's a trick to this. This is another one of those examples where it is a clever trick that I never would have thought of myself, probably, and you don't have to have thought of it yourself, so don't hold yourself to this, for this example would be a very high standard of, yeah, I can see how I would have naturally thought to do that. No, this is a very clever trick, and the trick is, when you have a domain that is a parallelepiped with one vertex at the origin, take those edge vectors, make those edge vectors the columns of a matrix, and that matrix in the usual way will define an awesome change of variables function. That's the trick. Cool trick. Edge vectors, make those the columns of a matrix. That defines linear transformation change of variables function. Okay. Now, I claim that's an awesome trick. How do I know that works? What does that do? What is the pullback domain in this case? And I claim the pullback domain is going to be just, let's see here, I've already forgotten what colors I've used. Okay, let me start over. The pullback domain is going to be the unit cube over here. Just the unit cube. So why do I know that's the case? And I'm going to show that by just thinking one edge vector at a time. Let's look at E1, for example. Sorry, pencil load. Let's look at E1 here. What is the image over here of E1? Okay, well, we're just going to plug into our linear transformation. In particular, that E1 is what goes into the linear transformation. That's what I'll plug in for you. The output, the image, let's see, I'll do the image in blue. The output, I just multiply by the matrix A. What do you get when you multiply a matrix times a standard basis vector? Now again, this is one of the cornerstone, most useful and fundamental facts about matrix algebra and linear algebra is that a matrix times a standard basis vector gives you the corresponding column. Right? So this image output vector x is the corresponding column. Oh wait, I cleverly arranged that corresponding column is the first edge vector that it's supposed to be. So that's why we do it that way, and that's why it works out so nicely. So likewise for E2 and E3, and then linearity argument, you can see that we get exactly what we want there. So super powerful trick, and we're basically in business at this point. And so again, we started off with this nightmarish scenario of a terrible domain over which we're doing an integral, and we pulled back through our cleverly arranged change of variables function, and now have as our new domain of our pullback integral the unit cube, which is awesome. World's most convenient domain for a triplet. How we doing? Everybody on board? All right, one other little detail that I'm going to mention, and again, I think it's a good exercise to think this through, but we do have to convert the z here. I've got to figure out how to rewrite z in terms of u, v, and w. Don't forget what z is. Z is your third output coordinate. So it's the third coordinate of that output. How would you compute that third coordinate of that output? What is the third coordinate of a matrix vector product? And if you punch that up, I claim that z ends up in this. So again, blanks to be filled in, but write down AU, multiply it out, look at the third coordinate, that's what it's going to be. And by the way, you'll notice here already that these coefficients are the third row, and again, you want to make sure you think through why that is the case. Yeah.
So the third coordinate is just the third row.
The coefficients are the third row, but think through why and make sure you're clear on why that's true. Yeah. Does that make sense?
Yeah.
Yeah. Good. Okay. Okay, so again, prohibitively difficult problem, and again, just for fun, I like to kind of think through how bad would this have been if we hadn't done a change of variables. Well, this is a parallelepiped. It has 8 corners, one of which might be the start, one of which might be the end. Okay, yeah, fine, fair. There are 6 corners in the middle that you're going to slice through. That means you're going to have 7 separate iterated triple integrals. But it's worse than that, because those cross sections are not rectangles. Those cross sections are, depending on where you are in the slicing, either parallelograms or possibly hexagons, maybe triangles, but they're not pretty, right? So each of those 7 is going to have to be broken up into several, typically 3, sometimes more, sometimes less. So we're talking 20 or more separate triple integrals. This is a nightmare if you do it the old-fashioned way. Change of variables, it's easy. Okay. Yeah.
How'd you choose like Z?
Yeah. So that's an exercise. So A is this. Multiply A times U. Identify the third coordinate. So that's something to work out. Yeah. All right. Okay, so on to the next thing. I'm going to call this integrals in coordinate systems. I want to slowly segue ourselves into this. I don't want to just start writing stuff down. So the way I like to think about this is that we are, in fact, doing a change of variables. So I'm going to present this as doing a change of variables, but with specific, very commonly chosen change of variables functions. And specifically, we're going to use coordinate conversion formulas as change of variables functions. It's a little bit weird to think. It's a kind of a, can you do that? But yeah, totally. You can 100% do that. So first example, y'all recall we talked about polar coordinates a long time ago, and I like to think of polar coordinates as being a function. And okay, sure, you can also think about polar coordinates as sort of a certain geometry that you look at points as, well, certain angles and distances, stuff like that. Sure, fine, right? But I think it's a little bit more convenient and elegant to just write it down as a function and then let your geometric interpretations flow from that. So there you go. This is a function that we've thought of as converting coordinates, but it also has 2 inputs and 2 outputs, and I can think of this as a change of variables function through which I might want to do a pullback. It's got all the necessary earmarks. So, okay, let's take that function. Let's compute its Jacobian determinant. And by let's, I mean you. Again, this is an exercise, right? Everybody should do this once in their lives. It's not a hard one. There's your formulas. Plug in, and calculation ensues. It's actually a pretty short calculation. It'll take you like a minute or something. And here's what your Jacobian determinant ends up being. It's R. And turns out we're going to be using this as a change of variables function loads in this class. So this is a calculation you should plan on doing once in your life, right? And then remember the answer, so you don't have to do it every single time that you want to use this as a change of variables function. All right, now you can do likewise with the other coordinate systems, right? So cylindrical coordinates, again, you can think of as a function. R, theta, z are your inputs, x, y, z are your outputs. Old formulas that we've known since the start, near the start of the course. Okay. Likewise, spherical coordinates. You can think of this as a function. Old formulas that we've known, again, going way back, chapter 1. Okay, so these 2, you can say, all right, given this function, what's the Jacobian determinant? Plug and chug. Everyone should do this once in their lives. This too will take you about a minute. It's not that tedious. Follow the rules, compute as indicated, you get R. And for spherical coordinates, again, that's plug and chug. You take these formulas, plug into the formula for Jacobian determinant. This one actually is a little bit more tedious. This will probably take you closer to 5 minutes. But again, everyone should do this once in their lives. Make sure you can do it. I don't remember when, but at some point, I think by this time, many years ago, I actually made this a test question to, do this computation right here. Anyway, for whatever that's worth. Anyway, I think it's a good calculation. Make sure you can do it. Okay, as always, come to my office hours. If you get stuck, happy to help. Okay, so back up to polar. There is a sticky point. This is a bother. But our Jacobian determinant is not the stretching factor. Sadly, the stretching factor is the absolute value of that. So what you're going to stick into your pullback integral is going to have absolute values in it. And that's terrible, right? None of our shortcut formulas for computing integrals, single variable anti-differentiation rules, none of them play nice with absolute values. So that's terrible. How are we going to get around this? And there's a clever and actually fairly convenient little way around it. We're going to make the choice. I emphasize choice. We don't have to. We do this for our own personal convenience. But we can choose to always restrict our attention just to positive values of R. And if we choose to do that, which I strongly advise that we do, choose to do this, R is now positive. The absolute value of R is now, in fact, no problem. It's just R. And the absolute values are gone. Is that cool? Everybody follow the choice there? So again, I have this quibble with how this is presented in a lot of contexts. A lot of people tell you when you do polar coordinates, R has to be positive. No, it doesn't. It really doesn't. And in fact, if you're not doing a change of variables where this absolute values arises, there is no need to make such a restriction, right? So I like presenting it this way so you can see why we make certain choices, and it's because of convenience, right? It's for a good reason, and I think it's important to understand that reason. Okay. All right. So ditto for cylindrical coordinates. By the way, you're going to notice polar and cylindrical do have an awful lot in common. Not only do the equations look a lot alike, the Jacobian determinant formula turns out the same. So the little workaround is identical, and again, you get the same eventual punchline stretching factor formula. Okay. Alrighty. Spherical coordinates, not so much. Spherical coordinates gets a little weird. Reminder, this is our Jacobian determinant. This is the thing whose absolute value we have to worry about, and how are we going to deal with that absolute value? What clever workaround can we do to make that absolute value go away? Common mistake, very common mistake students have been told, I guess, I don't know, by somebody, maybe even a high school teacher or something, that rho is kind of like R, and when you're doing spherical coordinates, you just kind of think R. When you see a rho, think R, and absolutely not. It's just not true. And this is a great example. What would have happened to our little quandary here, a little predicament, if I were to promise I will only pick positive values of rho? Does that help me? It doesn't. No, of course not. The rho is going to get squared anyway, for one thing, so who cares? Don't put any restrictions on rho. There's no need to put a restriction on rho. It doesn't buy you anything. What we need to worry about here, what's going to fix our problem, is we got to find a way to make sine phi positive, or at least non-negative. And that is easily arranged by making this choice right here. And again, choice. Don't have to, but we're doing so for our own convenience. Just make sure to always choose phi between 0 and pi. That'll make sine phi positive. That'll make the inside of this absolute value positive. That makes the absolute values disappear. Everybody happy? All right, good news. These are my favorite values of phi anyway. All right, so this is a win-win. We get a fantastic excuse, if nothing else, to restrict ourselves to the values of phi that were most convenient anyway, and also get the benefit of getting rid of these absolute values. So it's a total win-win choice there. Okay. All right, let's do one. Polar coordinates. We're going to start off looking at this region right here, first quadrant portion of the unit disk. That will be our domain for a double integral here. Now, specifically this double integral that we're interested in, if you were to take a section 5.2 approach to this problem, if you were to just slice it up, regular, rectangular coordinates as it were, this is what you get. And this is going to be a bummer. It's not impossible, but it's no fun. Because you can just look at this inside integral, you do the dy integral, you're going to have odd powers of y. So you're going to be taking an odd power of a square root, which means your new integrand is going to have ugliness in it. And you're going to have to do trig substitutions. And again, it's not that you can't do that, but it's that it's a lot of work and we don't want to. Right? All right, so undesirable. Neat fact, this domain is the image by way of our regular good old polar coordinates conversion formulas. It is the image of this rectangle right there. So now I'm gonna make an argument as to why that's the case. But before we do, let's take a moment to recognize how awesome that is. Then when I do the pullback, my domain, I can see my bounds are going to be easy because my new pullback domain is just a rectangle. We love rectangles. We get constant bounds. The integral turns out to be easy. So that's why we're doing this, right? That's why we already see this is going to be a huge victory, right? So let's check the details. Let's make sure that this works. And we're going to take this one edge at a time. I like to start with this one. What can I say about this edge? Well, you just look at the picture. We're in the r theta plane. This edge is where theta is 0, and r goes from 0 to 1. Now, think about what that looks like in the in the xy plane. Theta equals 0, r goes from 0 to 1. It'll be that. Likewise, this edge, r equals 1, theta goes from 0 to pi over 2. Keep that in mind. Now come over here to the xy plane. What does it look like if you stick to r equals 1 and let theta go from 0 to pi over 2? Well, then you get that. Everybody on board? Likewise, this edge, not hard to persuade yourself. Theta is pi over 2. That gives you this right here. Again, r goes from 0 to 1. The weird one is this last edge here. The left edge, that's where r equals 0. At which point it doesn't really matter what theta is doing. Right? If r equals 0, then in the xy plane, r equals 0 is, well, that's literally just the origin. It's a little bit strange. This region, when you plug it into this change of variables function, it's like this edge kind of gets pinched down, and then everything else kind of opens up like a fan, approximately. Does that make sense? Okay. Yeah?
Where does the R come from in the RDRD data?
Oh, yeah, well, I'll get to that in a second. Yep. Okay. All righty. So, so we've got a pullback domain. Now, the first thing I'm going to do is let's recognize that we do have an integrand. This is the plug-in part. Plugging in, keeping in mind that my function is just my conversion formulas. It's my polar coordinate conversion formulas. All I got to do is convert this into polar coordinates. And x squared plus y squared, we've long established, is r squared. So that part's easy. This right here, dA, represents a piece of area in the xy plane, and that piece of area in the xy plane is going to be a factor times area in the r theta plane, and that factor, the area stretching factor, by way of the polar coordinates conversion formula we saw on the previous page, that stretching factor is r. So that's why we get it's just the stretching factor. We are doing a change of variables here. How we doing? Everybody's happy? Okay. All right, sweet. So we're in business, and just clean up here. Super easy integral. Now, you got to be careful about one thing. It is common to insert the stretching factor in there dutifully, and then to somehow be scared to do anything with it, like, oh yeah, but it needs to be there. Yeah, true, it does need to be there, but it needs to be there in order to be part of, in fact, my new integrand. My new integrand is not r squared. My new integrand is r cubed. Right, so don't forget, that's what the stretching factor is there for. It's to account for the factor difference in the areas of the sort of the differentials, if you will. So r cubed is our integrand, easy antiderivative, plug in the numbers, et cetera. Computation goes through very easily. Final answer, pi over 8. Details to check, and make sure you can do that, right? But anyway, that's what I got anyway. I hope that's right. You see how nice that is? It's so much nicer than the alternative. I mean, it's not that you can't do trig substitutions and whatever else might be necessary to make this work out, but that's a lot more work. It's way easier to do the pullback. Okay. All righty. So this is fine. Nothing wrong with this. But we can make this better. We can make this more streamlined. We did have to kind of spend a little time thinking about this edge goes to there and that edge goes to there. And that kind of presumed that I already knew what the pullback domain was. I already knew what edges to be checking in the first place, right? So in practice, how can we make this a little bit more convenient so I don't have to intuit the new domain and then check that the edges work out and all that kind of stuff? So here's the clever observation. You can actually see all of the slicing that you're doing in the r theta plane. You can see all of that in the xy plane. You don't have to draw the pullback. So in particular, whatever your domain is here in the r theta plane, whatever that is, whatever that came from, oh gosh, can I draw I don't know, something like that, our original domain, yikes, something like that maybe. Well, every slice that I do here, every theta slice, remember a theta slice means constant value of theta, I can tell you exactly what that looks like right here in the xy plane. And that is, well, it represents constant value of theta. Constant values of theta in the xy plane look like this. They're just radial slices. So all of the slicing that I did over here, so for example, we let, let's see here, we let theta go from 0 to pi over 2, so we were doing theta slices like this. All right, I can see them right here. Those theta slices look something like this. Right, my very first theta slice that gives me my initial theta bound, yeah, there it is. That right there. And I can easily see, right here in the xy plane, I can already see that first theta slice is where theta is 0. And likewise, this last theta slice that gave me my upper bound of pi over 2, well, there it is. Here in the xy plane, I already see it. That's clearly the last one of these kind of radial slices. That's clearly where theta is pi over 2. I get the same result. while still looking in the XY plane. I don't even have to look into the R theta plane. Everybody buy it? So that's the big insight, and with that in mind, let's do this example all over again. Now this is the same exact example, and I literally copy-pasted the picture and everything, and then I added, some additional annotations. But same domain, same undesirable integral, pulling back again, but this time, even though we are doing a pullback, we're not going to look at the pullback. Everything that we might need to know about the pullback, we're going to infer from right here. In the XY plane picture we already have. I don't need to generate a whole new picture over here on the left just to draw conclusions about it when I can draw conclusions about it from right here. And so that's what we're going to do here. Let's see here. We know that x squared plus y squared is r squared. No picture required for that. That's just formulas. We know that our stretching factor is r. Again, no formulas required for that. We already punched that out. The only thing that remains is the bounds. How am I going to find the bounds? Well, theta. Okay, granted, technically, theta bounds come from theta slicing over here, but I can see all of those slices right here in front of me, and the first slice is clearly there at theta equals 0, etc., 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 etc. The last slice is going to be there, which is clearly pi over 2, like so. I don't even have to look at the left picture. And if I don't have to look at it, I don't have to draw it. Does that make sense? All right, now what about the inside bounds? Remember the way we do inside bounds, we fix a value of the outside variable, so I'm going to fix a theta slice. And let's think about first and last. Okay, well, here's the first point on that slice, that theta slice. I want to know what's the value of r at that point, at the origin. R equals 0. No problem. All right, now my last slice, as I proceed, along this theta slice in the r direction, let's see, my last value of r, well, it's going to come from that point. That's my last point. That point is on this curve. That curve in polar coordinates has that equation. Notice I'm following our usual process. We identify a point. Identify what curve it's on. That curve has an equation. Now we're going to solve for the variable we're interested in. We're interested in r, so we solve for r, and we get r equals 1. Same result. Didn't have to draw the pullback at all. Everybody see how that works? Any questions? Feel free. All right, it's a real slick move. Streamlines the process quite a bit. Morally equivalent to what I did up here, just faster, easier. Okay, so here's another example. By the way, just a little bit of terminology. What I did here, let's not lose sight of the fact, this is a change of variables. I am doing a pullback. That's where this whole stretching factor thing came from in the first place. Legitimately, this is a change of variables, 100%. I just don't have to think of it that way. So when we do a change of variables using a coordinate system conversion formula as the pullback function, and when we visualize what we need in the XY plane without drawing the pullback domain, that's called doing an integral in polar coordinates is the term. So casually speaking, people will call it, well, we did this integral in polar coordinates. This is the result. Okay, another example. What if our domain is the entire unit disk? Like so? Well, now again, look, you can draw the pullback if you want, but it's unnecessary artistic challenge. There's kind of no reason to. I think it's just much easier to observe that as we do our theta slices, you see I'm doing my d theta on the outside here. As I do my theta slices, well, the first one, let's say, is there where theta equals 0. And then I kind of go all the way around, as it were. I mean, these are my theta slices, and those theta slices just go all the way around, et cetera, et cetera. And then I'm going to be done when I get back where I was in the first place. Common mistake to make is for people to think, well, let's see, I'm back going the same direction, and same direction would mean the same value of theta. A lot of people would put 0 as the upper bound also, but no. Theta has been increasing steadily throughout, right? Remember, there actually is a pullback domain, and so in order to make that pullback domain not nothing, okay, theta's got to be 2 pi. That's what I've grown theta into by going all the way around. So the upper bound then is 2 pi. Everybody happy with that? So nice little thing to remember when your domain goes all the way around. So this is one way to think about it. The slices go all the way around. I also like to sometimes think about this as when the domain entirely surrounds the origin. Right? If the origin is in the interior of your domain, well, then the theta slices are going to have to go all the way around. And when that's the case, your theta bounds are just 0 to 2 pi. All right? All right, the rest of this example is pretty straightforward, I think. So make sure to read through all the rest of this and make sure that you're good with all those details. Okay, now several more examples to follow, but there are a couple of little tips and tricks that I think are really nice, so I hope y'all will find these convenient. You do have 2 choices for how to order your differentials, and here's the good news. It is basically always, not quite always. There are some weird, heavily manufactured, unnatural counterexamples. But in the real world, organically speaking, it's basically always the case that this is the way you should order your differentials. Just always do it like this, and the time you will save by not even considering the other ordering will dramatically offset any possible benefits of conceivably you might encounter a situation where there's something to be gained the other way. It's practically impossible. So always do this, dr d theta. Let's see here. This is just a strategic one here. And by the way, I include myself in the following group. There are plenty of people, again, myself included, who will find themselves distracted by thinking about the slices and the starting and ending and then which points and what curve and this equation and I need it in polar coordinates and converting the equation. There's a lot of little details going on. And then we'll forget to stick in the stretching factor. Oh my gosh, so easy. I've done it many times, over many years to be fair, but still I've done it many times, right? And super easy to get distracted and forget. So my hack, little personal problem solver on this, is that I always write down the R at the same time that I write down the differentials. I always, at this point going forward, I always write down R dr d theta all at once. I never write down dr d theta in solving a problem without having the R instantly written down there at the same time. Right? And if you make this just do a little ritual, this is a little rule you follow, that will help you to not forget and then have to deal with the consequences. So I hope y'all will follow this rule. By the way, just if only from a strategic standpoint. So let's talk about exams. Right? So on an exam, I've got a grade based on what's written on the page. I can't assume, right, that you know stuff that isn't represented on the page. I just can't, right? This would be fair. And if you think about it, this R, being as it is the stretching factor, if you think about it, being the most sophisticated part of the process, right? That's the hard part, is figuring out what the stretching factor is. This R, this one little character by itself, several points, right? Depending on the question, depending on how much else is going on, could be anywhere from 3 to 5 points for that one character, right? And in fact, I'm pretty sure I remember years ago, there was a question, some double integral to be solved on an exam, and there was one student that did not know how to do the problem, right? But the student wrote down blank page except for RD theta. I think that student got 4 points for that, right? So don't leave money on the table. Write that down. Get those points, right? Get those locked down, right? Don't just, I'll remember. I'll get those points later, right? That's a bad plan. You just might forget, and why take the chance? Okay. All right. Okay, and then as every other kind of integral we've ever done, how do you find the bounds? Well, you identify the relevant points. Those points you identify as being on relevant curves. Those curves have a relevant equation, which you then solve to find the bounds. Okay, so let's do some more. I like this one because of how unexpected it is to need this. So integral to be done. Our domain is this, what we call an annulus. Wrong. Sorry. I got into coloring mode. Just this part, like this. I don't know why I think of this as a moat around I imagine a little castle right here. I don't know why. And anyway, so if that's the domain for your integral, how would you compute this integral? And you do have options. Now, a clever move, or at least a clever thing to try, that students do sometimes, is to say, okay, well, I'll tell you what, I'm going to compute the integral on the entire disk, and then I'm going to subtract what I would get for the integral on just the island part there. So yellow minus purple, right? And it's tempting to say, well, hey, yellow minus purple gives me the annulus, and so cool, right? No problem. There's a serious problem here. The problem is that if you look at the integrand, and details matter, this integrand is not defined at the origin, and not in a nice way. This has a vertical asymptote, right, at the origin, which means that the integral is simply not defined at all on any domain that includes the origin. So that integral not defined, that integral is not defined. So this is a bunch of garbage nonsense. You just can't do it. Does that make sense to everybody? Yes. Annoying, but anyway. Okay, so fine, that clever idea aside, let's do this brute force. Let's slice it up. Well, of course, you're going to hit a little corner there. Weird stuff happens there. And then, so you say, okay, well, I'll do the bottom edge, and then I will separately do the top edge, or the top part there. And then, again, there's a point there, and so we'll finish up the last little bit there. You notice you get 4 separate iterated integrals. That's no good, right? Clearly suboptimal. By the way, they're hard integrals because look at these edges, right? The edges here are circles. Circles means there's going to be square roots in your bounds. That means these are hard integrals. So we don't want to do that either. So look how easy the alternative is. Just do it in polar coordinates, right? In polar coordinates, notice we go all the way around, so theta is 0 to 2 pi, as previously noted. For any theta slice, R starts at that point, which is on that curve, which has that equation, following our little procedure, right? Solve for R. Don't forget what you're looking for. We solve for R, and we get 1. And then let's see, we end R at that point, which is on that curve, which has that equation, which again, we solve for R, and you get 2. Turns out to be an easy integral. We don't go anywhere near the singularity. Everything's perfectly well defined, no problem, easy answer. Way, 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 way better than this option. And of course, this isn't an option in the first place. Yeah.
Where does the 1 over R?
Yeah, so that's the integrand. So remember our integrand. Yeah. Right. Yeah. Right. Yeah.
We have that question about, is there ever like a non-circular domain that you'd use like polar coordinates on? It's not like a perfect circle.
Ever is a scary word to a mathematician. Let me think about that for a second. I could dream something up, probably. I'm not prepared to give you an example at the moment, but certainly I'll agree with the spirit of your question. When you see circles in your domain, that is a tip-off that polar coordinates, quite possibly a great choice. That part, absolutely true. But yeah, I hesitate to say always. Yeah. Okay. Now here's a harder example. Now again, this satisfies the circle rule that you just noted. So our domain here starts off by looking at this disk, and let's see here. Then we're going to exclude any of those points that are in this disk. So green, but then get rid of any point that's in the blue. And the punchline, of course, is that our domain is this kind of solar eclipse region right there. Yeah. Okay. Well, here's what a theta slice looks like. Keep in mind, theta slices always emanate out of the origin. So there is a, for example, value of theta, and here's the resulting theta slice. Notice that theta starts here. Let's think about that point before we go to the end point. What's the value of theta at that point? Really clever observation. Again, I benefit from my teachers who benefited from their teachers, etc. Check this out. That edge and that edge are radii of this circle, which is clearly a circle of radius 1. And this edge is a radius of this circle, which is also a circle of radius 1. That means we have ourselves a little equilateral triangle right here. High school geometry tells me what that angle is. And of course, as a polar coordinate, I know that that angle is negative. And so negative pi over 3. It's a slick move. Be on the lookout for this kind of thing. It comes up, I'm going to say surprisingly often. Little clever opportunities in geometry like this. So the other thing about this example that I want to point out, by the way, likewise for the upper bound, right? Similar argument. Make sure you can do that. The other thing I want to point out is how to find your R bounds. So we're going to pick a theta slice like so, and let's look at the upper bound because I know we're short on time. The upper bound is going to come from that point, which is on that curve, which has an equation that looks like this. But I need to solve for R because I'm looking for an R bound. How do I solve for R? This isn't in polar coordinates. So you've got to convert. Right? So good news, we know how to do that. Flashback to chapter 1. We talked about how to convert equations from rectangular coordinates to polar coordinates. This is, in fact, converts like that. And proceeding, solve for r. That's your bound. Is everybody good with that? Okay, so we'll draw the line right here. Y'all have a good rest of your Wednesday. See you on Friday. Don't forget about attendance if I didn't already get you. Just a second.